Welcome back to the deep dive. Today, we're jumping into something fundamental. I mean, literally, the force that powers almost everything we touch electricity. We're not just going to skim the surface with definitions, though. Our mission here is to really get into the structure, the mechanics of how power works, how it flows, and maybe most importantly, how we measure efficiency and where that efficiency sometimes breaks down. Think of it as going from a single electron's push right up to the big picture economics of the power grid.
Exactly. And most people have heard the terms, right? Voltage, current, resistance.
Mhm.
But the really interesting stuff, the deep dive, starts when we look at the flow itself. So DC versus AC. And then especially with AC, you get into these complexities like power factor. That's where you see huge differences in cost, grid stability, all of that. We really want you to walk away understanding not just what power is, but how you actually gauge its true efficiency.
Okay, sounds good. So let's unpack this. We probably need to start with those three core ideas first, just to make sure we're all on the same page for analyzing any circuit. If we think about electricity like, say, water in pipes, how do voltage, current, and resistance fit in?
Yeah, the water analogy is perfect for this. We can probably cover all three pretty quickly. So think of the whole setup as a water pipe. Voltage V. That's like the water pressure. It's the electrical potential difference. It's the push, basically, that makes the water want to move.
Okay, pressure. Got it.
Then you've got current die. That's the flow rate. How much water, or in our case, electric charge, is actually moving past a certain point per second.
Right, so the amount flowing and resistance. If it's like water, resistance must be, what, the pipe size?
Yeah.
Something slowing it down.
Precisely. Resistance R is the opposition to that flow. Think of it like a narrow pipe, or maybe some rough texture inside the pipe, or even a kink in a hose. Anything that makes it harder for the water to flow. So smaller pipe, more resistance. And the key thing is these three are totally interconnected. You can't really talk about one without the others. The pressure causes the flow, and the resistance limits how much flow you get for that pressure.
That relationship, okay, that makes sense. It's the basic physics setting the stage for everything else.
Exactly.
So now we have V, I, and R. Let's talk about the direction of flow, because this is where things split fundamentally, isn't it? Between like the power in my phone battery and the power coming out of the wall socket, direct current, DC, versus alternating current, AC.
Right. DC direct current is the simpler one to start with. The charge, the electrons, they flow in just one direction consistently. And the voltage, it stays pretty much constant over time. Think batteries, solar panels. Those are your classic DC sources.
And that steady one-way flow is absolutely vital for almost all our electronics, yeah?
Yeah.
Laptops, phones, tablets, they need that smooth, low-voltage DC supply.
Oh, absolutely. The microchips, the processors, all those tiny components inside modern gadgets, they rely on that super stable, unchanging DC power. Any big fluctuation, any reversal, it could fry them instantly. That's why you always have that little power brick or the adapter built into the plug. The whole job is converting the AC from the wall into the clean DC the device actually needs.
Okay, so DC is for the devices, but then here's where it gets really interesting, like you said. The power delivered to our homes, the stuff running the big appliances, the lights, that's alternating current AC.
Wow.
Why? Why did the world standardize on a type of electricity that literally flips directions, 50 or 60 times every second? It seems counterintuitive.
Well, it seems that way, but the reason's all about efficiency. Specifically, efficiency of transmission over long distances. With AC, the current and voltage aren't constant. They vary, usually in a smooth sine wave pattern, flipping polarity back and forth. The magic trick with AC is the transformer. Because the voltage is always changing, you can use a relatively simple transformer to step that voltage way up.
Up to like hundreds of thousands of volts, right?
Sorry.
For those big transmission lines.
Exactly. And when you crank up the voltage that high, you could transmit the same amount of power with much, much less current. Less current means way less energy lost as heat in the power lines. Think I squared R losses. So it's incredibly efficient for sending power across states or even countries.
Ah, okay. So AC is like the long-haul truck for electricity. High voltage, low current minimizes loss. Then you get it where it needs to go.
And then you use another transformer to step the voltage back down to a much safer level, the 120 or 240 volts we use in our homes and businesses. DC just can't do that step up, step down thing easily or cheaply. You need complex electronics, which historically weren't feasible on a large scale. So AC won the war of the currents for transmission.
Got it. It was a practical decision, really, logistics.
Pretty much.
Okay, so if V, I, and R are fundamentally linked, there must be a formula, right? A way to calculate how they relate. And that brings us to Ohm's law.
Yes, Ohm's law, named after Georg Ohm, who figured this out way back in 1827. It's incredibly important, but also beautifully simple. It just mathematically states the relationship we talked about. Voltage is the product of current and resistance, so the formula is just V equal I ER.
Voltage in volts, current in amps, and meris, and resistance in ohms, symbolized by that omega symbol, A. And you can rearrange it, right? If you know the voltage and resistance, you can find the current.
Exactly. That's often how it's used in practice. I equals VR. Or if you need resistance, R equals VI. Let's try that quick example from the source material. It makes it really concrete. So you've got a simple circuit, maybe a flashlight. It has a 12-volt battery, that's V, and the light bulb filament has a resistance of, say, 24 ohms. That's R.
Okay, 12 volts pushing, 24 ohms resisting.
Mm.
We want to find the current, so using the formula, I equals V divided by R. That's 12 volts divided by 24 ohms.
Which gives you 0.5. So
Yeah.
I equals 0.5 amperes. Half an amp of current flows through that light bulb filament.
Half an amp. And what does knowing that number actually let us do? What's the implication?
The implication is design and safety. If you know the voltage source and the resistance of the components, you can calculate the current. That tells you, for instance, what size wire you need so it doesn't overheat,
Oh.
or what fuse rating to use to protect the circuit. It allows engineers to build circuits that work reliably and don't, catch fire. Ohm's law basically says if you want more current, you need more push voltage or less resistance. It's fundamental for analyzing pretty much any DC circuit.
Okay, that makes perfect sense. Now, let's pivot back to AC, because you mentioned things get more complex there. We're moving beyond just VI and R into talking about power itself, and apparently not just one kind of power, but three. This sounds like the power triangle thing.
Yes, exactly. This is where AC power analysis gets, say, more interesting. In a simple DC circuit, power is straightforward.
Yeah.
Power in watts is just voltage times current. P equals VAI. Easy. But in AC, because voltage and current are constantly shifting, sometimes out of sync with each other, it gets more complicated.
Yeah.
We have to break power down into three components: active, reactive, and apparent power.
Okay, three types. Let's start with the easy one, hopefully. Active power.
Active power P is the one that makes the most intuitive sense. This is the power that actually does useful work. It's the energy that gets converted into heat, light, or mechanical motion, like turning a motor shaft. This is what you're typically billed for on your electricity bill. It's measured in watts, PDU, sometimes called real power or true power.
Okay, the work horsepower, watts, got it. But then, these other two, reactive and apparent power, they sound less straightforward. What's reactive power Q doing if active power does the work?
Right. Reactive power is a bit strange. It doesn't actually perform any useful work itself, like generating heat or light.
Right.
Instead, it's the power that's needed to create and maintain the magnetic fields in devices like motors, transformers, and inductors, or the electric fields in capacitors. Think of it as energy that sort of sloshes back and forth in the circuit. It's stored in a field one moment, then released back to the source the next. It's essential for the operation of certain equipment, but it doesn't contribute to the final output work. It's measured in VAR, which stands for volt-amps reactive.
Hold on. If it doesn't do useful work, why do we even need it? Why does the utility have to supply it?
Well, because without it, those inductive and capacitive components just wouldn't function. A motor needs that magnetic field to spin. A transformer needs it to transfer energy. So reactive power is like the overhead cost of enabling certain types of electrical work. It's necessary for the system to be ready, even if it's not the work itself.
Okay, it's like setup energy. That helps. So that brings us to the third one, apparent power S.
Apparent power is basically the total power that the utility grid has to supply to make everything work, including both the useful active power and the sloshing reactive power. It's the vector sum of P and Q. Think of a right-angled triangle. Active power P is one side, reactive power Q is the other side, and apparent power S is the hypotenuse. It represents the total strain on the system, the total capacity needed in wires and transformers. It's measured in VA, volt-amps.
So if my factory pulls, say, 100 kVA of apparent power from the grid, but only 80 kilowatts of active power is actually running the machines.
Then the remaining difference, calculated using the Pythagorean theorem essentially, S equals P or a P plus Q, represents the reactive power, in this case 60 kVAR, that the grid also had to supply just to keep your motor's magnetic fields energized.
Wow. Okay, so the grid is supplying power that isn't directly doing work. How do we measure how efficiently that's happening?
That's precisely where the power factor comes in. Power factor is simply the ratio of active power, the useful stuff, P, to apparent power, to the total supplied S. Power factor equals PS. It's a number between 0 and 1.
So a power factor of 1 would be perfect, right? Meaning all the power supplied, S, is doing useful work, P, And there's no reactive power queue.
Exactly. A power factor of 1 or 100% is the ideal. It means your load is Curie resistive, like a simple heater. But many loads, especially motors, are inductive. They require reactive power, which lowers the power factor maybe down to zero point 0.8, zero point 0.7, or even lower in some industrial cases.
And what's the big deal about a low power factor, say be at zero point 0.7? Why does that matter in the real world?
It matters a lot, especially for large consumers and the utility. A low power factor means you're drawing more current from the grid than you actually need for the work being done. Remember, apparent power S determines the total current. S equals VEI. So if S is much larger than P because of lots of Q, you're pulling excess amps. Let's take that factory example again. If it has hundreds of big motors, it needs a ton of reactive power Q. If its power factor is low, like zero point 0.7.
Then for every 70 kilowatt of useful work, it's actually pulling 100 kVA of total power from the grid. That extra 30% or so is just for the reactive power.
Precisely. And that extra current stresses everything. It requires thicker wires, bigger transformers, larger generators at the power plant. It increases energy losses, heat in the transmission lines. The utility hates low power factor because it reduces the capacity of their grid to deliver useful energy.
So they probably penalize customers for it, right?
Oh, absolutely. Large industrial and commercial customers often face hefty penalties on their bills if their power factor drops below a certain threshold, maybe zero point 0.9 or zero point 0.85. The good news is you can fix it. The common solution is to install capacitor banks at the facility. Capacitors supply reactive power locally. So instead of drawing all that Q from the grid miles away, the capacitors provide it right where the motors need it. This brings the overall power factor closer to 1, reduces the current drawn from the utility, and saves the factory money. It's called power factor correction.
That's fascinating. Optimizing based on power that doesn't even do work.
Yeah.
Okay, one last piece on the supply side. How does AC power actually get delivered? We see different kinds of power lines. What's the difference between single-phase and three-phase power?
Right, this is about the physical delivery system. Single-phase power is what you typically find in homes and small businesses. If you look at the wires coming to a house, it's usually 2 hot wires and a neutral, or sometimes just 1 hot and a neutral plus ground. It operates at lower voltages, like 2240V in North America. It's fine for lighting, computers, small appliances, most residential stuff.
Okay. And then the bigger setups, like factories or large buildings, they use three-phase power.
Yes, 3-phase is the standard for anything industrial, commercial, or involving large motors. It uses 3 conductors, or sometimes 4, with a neutral. The key difference isn't just higher voltage capability, it's how the power itself is delivered. You have 3 separate AC sine waves, but they're offset from each other. They peak at different times, specifically 120 degrees out of phase.
Ah, so instead of one pulse of power going up and down, you have 3 overlapping pulses, giving you a smoother, more constant delivery of power.
Exactly. That staggering means the total power delivered is much more consistent. It never drops to zero like single-phase power does momentarily in its cycle. This makes it way better for starting and running large motors smoothly and efficiently. They get more constant torque, less vibration. It's just a more robust and balanced way to deliver significant amounts of power.
Okay, that covers a lot of ground. We went from the absolute basics, VIR, through the crucial DC versus AC split, applied Ohm's law practically, and then really dug into the complexities of AC power with the power triangle and power factor. So wrapping this all up, what's the big takeaway? Why should someone listening care about all this beyond just, knowing how their toaster works?
Well, I think the takeaway is that understanding these fundamentals is key to seeing how our entire electrical world is designed for safety, efficiency, and reliability. And especially grasping concepts like reactive power and power factor. It shows that energy efficiency is more complicated than just looking at the watts on an appliance. It's about how effectively the entire system delivers the power needed. Minimizing that invisible reactive power is a huge part of optimizing energy use on a large scale, reducing costs, and lessening the strain on the grid. It's about understanding the difference between the energy you use and the energy the grid has to supply to let you use it.
That's a great point. It connects the dots. So here's something to think about. We look at our electric bills, we focus on the kilowatt hours, right? The active power we consumed. But beneath that number lies this whole hidden world of apparent power, reactive power, and power factor. There's an invisible cost and inefficiency baked into the system just to maintain those magnetic fields, just to be ready to do the work. Next time you hear about industrial efficiency or grid upgrades, think about that power factor. Consider all the energy needed just to keep the potential alive. What other invisible infrastructural costs are built into the systems that support your daily life, hidden just below the surface?